I'm Giulio Pasquale, and I'm excited to present you ChainReactor, automated privilege escalation chain discovery via AI planning. This is a joint work between King's College London, University of California, Santa Barbara, Vrije Universiteit Amsterdam, and University College London. We are all familiar with the single-step exploitation, which is assuming that we have an initial foothold on a system with an unprivileged shell. We might find a strong primitive, such a kernel exploit, to gain then a root shell. But what happens if we don't have such a strong primitive? Well, in that case, we might have to find vulnerabilities, satisfy the preconditions to exploit the vulnerability, then exploit it, but then at that point, this might not be still enough to gain root. So we might pivot to something else, to another problem on the system, which might be, for example, corrupting a systemd service that then is going to gain us access to a root shell. What we propose is a ChainReactor that aims to propose like a zero-click approach to automate these steps. ChainReactor is now open source, available on GitHub, and it's our automated system for identifying multi-step privilege escalation vulnerabilities. But before going forward, let's take a look at what are the requirements to find such chains. First of all, assuming that we have an unprivileged foothold on the system, we need to understand what's on the system itself. So we try to extract what we have: binaries, users, permissions, files, whatsoever. That is defining an initial step for our search. Once this is done, we need to determine ways on how to use this information, and that is defining actions to modify at this time the state of the system to progress with our search. Finally, we have to reason on what we found and the actions to reach our goal. That is, using a planner to find a path to the goal. ChainReactor is split in three components: the extractor, the encoder, and the planner. Let's go step by step. The first component is the extractor that, once connected to a target system, is going to extract the system information for later processing. The information that we extract is users, groups, executables, files, setuid executables, permissions, and so on. Then we map all the executables found with broad capabilities, such as writing a file, reading a file, uploading a file, and so on. We use the database, the GTFO binaries, and a manually curated list that is not a huge effort. It's a one-time effort to do such kind of mapping. And finally, also we try to map if there are any binaries that might be susceptible to CVEs according to their versions. For example, here we have a minimal system, for example, with two users, like user and root, and three binaries, vim, nano, and a system daemon in its script with their owner and permissions. Then this information is passed to the encoder that is going to generate a PDDL problem for later processing and solving. So let's go back for a second at the example that I showed you before, and now we can take a look at the facts that are generated in PDDL. So the users are going to be bound by the fact user, and also now the binaries are going to have multiple facts associated with them. For example, that they can write a file, their owner, and their permissions. This is a minimal PDDL problem. This is how it looks. And it's split in three main parts: the objects, the initial state, and a goal. The objects are the bricks that we can use, for example, the files, executables, and the groups. And then the init state is a set of facts that link this object with properties on the system. And finally, importantly, we have the goal that we want to reach, in our case, to control root. It's important to note that the goal state does not define how to exactly achieve the goal, but just the desired outcome. So there is no fixed path, and the PDDL planner is free to explore multiple routes to reach the goal state. And so this allows to different solutions to be found, if any, on the system. But how do we actually get to the goal state? In this case, this is done via actions that modify the state of the system. And this is done by the PDDL domain actions. So the actions are the planner's transitions to bring the planner from one state to the other. The structure is basically taking parameters, precondition, and effects. The parameters can be seen as function arguments. Preconditions are the facts that have to be satisfied such that the action can be taken, and then the effects are the facts that are going to be present in the modified state. This is an example of an action that is write data to file. So to write some arbitrary data to file, we want that it must be an executable that can write to a file, that the user spawning such a process associated to the executable can write to the file, and then as an effect, the file that we are targeting is going to contain arbitrary data D. This can be used, for example, to corrupt binaries or files on the system with shellcode or whatever. The final step is the planner. So we take the PDDL problem, we take the domain, and then give it to the planner that is going to generate the chain, if any is present. The planner that we use is Powerlifted, is an open source planner that won the International Planning Competition of this year. And it's also available online and open source. So let's take a look now what the planner does to derive step by step the plan to get to our goal state. So we start from our control user being user. Then by using the action spawn process, it's going to use vim that can write to a file. Then via writing arbitrary data that is corrupting, in this case, the system daemon, the init script is going to inject like arbitrary commands. And finally, we can pivot to the control user being root. But as I showed you earlier, the goal state doesn't dictate the exact path. So if we take a look, the planner can also choose to use nano if, for example, one of the two binaries is not present, or to find other ways in such a way that we can write to a file and achieve the same consequence. Now let's move to the results. To reiterate, given an initial foothold on the system, can we escalate to root with no interactions, with a zero-click approach? We tested our approach on 3 CTF VMs. First, to test our approach and also to check that as we continued developing, our approach kept working as intended. We were able to exploit all of them in multiple ways. And then we wanted to challenge the tool with real-world scenarios. And we tested ChainReactor on 500 Amazon instances and more than 150 DigitalOcean instances. And we were able to find 20 0 days. On average, also it took slightly more than 15 minutes. 4 on DigitalOcean and 16 on Amazon. We reported all the chains to the vendors and have been in contact with the vendors since then. And also Amazon removed 2 of the images from the marketplace after our reports. So in conclusion, I presented you ChainReactor. We tested and found 0 days on more than 700 cloud instances. And it's open source, and the artifact is available, functional, and reproduced. If you have any questions, I'm here to answer them.